Today's video will introduce you about Compton scattering. Arthur Compton discovered that when a beam of X-rays incident on a metal, they scattered from free electrons in the metal. For some of the scattered X-rays, they had the same wavelength as before, but for the others, the wavelength increased. It was also found that the increased wavelength was dependent only on the scattering angle. This phenomenon is what we call the Compton effect. However, this is contradictory to classical electromagnetism, which predicts that when light with frequency nu0 passes through an object, it causes charged particles in that object to vibrate at same frequency, and therefore produce light at same frequency nu. The phenomenon could be explained by quantum light hypothesis. The photon collides with a free electron in outer shell and passes partial energy to it. The electron gains energy and ejects from its original orbital position. According to the conservation of energy, the increasing in energy of electrons makes the energy for the photon to decrease. Therefore, the wavelength of photon increases based on the equation E equals to hc over lambda. But why would some scattered X-rays remain the same frequency? In this case, the photon collides with an inner electron which is held tightly to its atom. The energy is transferred from the photon to the whole atom. Since the mass of atom is much greater than that of a photon, the energy change of a photon can be ignored, and therefore the wavelength is unchanged.
This is a simple diagram of what you guys saw in the beginning, where the energy of the photon decreases after the collision depending on the angle of scattering, and we describe this effect using the Compton shift formula. We can see from this that the change in wavelength is dependent on the angle, where the Compton wavelength lambda c is equal to the Planck's constant divided by mass and the speed of light. In this case, m is the mass of the electron. We get this by getting an expression from the conservation of momentum and conservation of energy, and equating them. So with conservation of momentum, we have it that the momentum before equals the momentum after. So the photon's momentum before equals the momentum of the photon after, plus the momentum of the electron after. The electron has no momentum before since it's not moving. So therefore we have P1 equals P2 plus PE. And then we rearrange to get PE and then square both sides to get PE squared. We'll then equate this PE squared to the expression for PE squared we derive using conservation of energy. Energy is pretty much the same ballgame as momentum here, with it being conserved and all. So we get E1 plus E0 equals E2 plus EE, and we get these energies from this equation from special relativity that has a kinetic energy and a rest energy term. We can get rid of the rest energy term for photons since they have no mass, and we can get rid of the kinetic energy term for the electron before since it has no momentum. For the electron after, it has the whole shebang, and has PE squared, which is basically the link to what we found using conservation of momentum. We won't derive it here because we have no time, but you can try for yourself if you're enthusiastic. I'll give you EMP, which you basically manipulate to eliminate U, and gamma is the Lorentz factor. Now, onto the derivation speedrun. Oh my dear, that's a lot of boring algebra. It's quite fast, so if you'd like to follow each step, I suggest slowing the video. But all we're doing is rearranging and squaring terms to equate PE squared to the expression we got for PE squared earlier, which is in red. Then we rearrange to get 1 over P2 minus 1 over P1 equaling whatever, so that when we multiply by Planck's constant, we can obtain the wavelengths. How do we know this? E equals hc over lambda equals Pc, and then we rearrange to get h over P equals lambda. So we use this, and what do you know? Bada bing, bada boom, we got Compton scattering formula.
Where did this complex mathematics lead us to? Now let's look at the result of Compton scattering. These graphs are showing the intensity of light at different wavelengths after the Compton effect, at the angles of 0, 45, 90, and 135 degrees. As you can see, the amount shifted increases with the angle, just as expected from the equation. At the angle of 0 degrees, we have the peak at lambda naught, since the light is unshifted. If we look at the non-zero angles, we have two peaks. One of the peaks is at lambda prime, which is predicted by the Compton shift equation. We also have another peak at lambda naught, which is caused by the light interacted with bound electrons and shifted by a negligible amount. Both Compton scattering and photoelectric effect occur due to the interaction between photon and atom. What causes the difference? In Compton scattering, the energy of the photon is much higher than the binding energy of electrons, so photons still have energy by itself even after the collision. However, in case of photoelectric effect, the energy of the photon is only slightly higher than the binding energy, so the photons are absorbed by the electrons. All the energy of the photon will be used to overcome the binding energy of electron and convert it to electron's kinetic energy.
One application of Compton scattering is its use in both radiotherapy and diagnostic X-rays. X-rays, which are simply high-energy photons with small wavelengths, are fired at free electrons, and as you have seen, a scattered photon with a lower energy and a recoil electron, now with kinetic energy, are produced. Radiotherapy, designed as the treatment of diseases, especially cancer, using X-rays or similar forms of radiation, uses this change in energy of the scattering to kill cancerous cells. Once the instant X-ray has transferred some of its energy to the free electron, the electron then excites or gives energy to neighboring atoms. This extra energy that the atom contains is transferred into thermal energy, and so heat is produced. When hot enough, this heat can cause biological damage, which is usually not what you want. However, when a patient has a cancerous tumor, targeted Compton scattering on the area affected can kill the cancerous cells without surgery. The scattered X-rays simply go on to interact with more free electrons but at lower energies, and the process continues. So if Arthur H. Compton had never discovered Compton scattering, we would never have to derive long, complicated expressions in second-year physics, but we also wouldn't have a way of treating cancer. So well done, Arthur. Our short-term pain is others' much more rewarding gain. If you have any questions on this topic, please feel free to comment below and we will answer your queries. Thank you for watching.